So let's actually start with how Draco tooling is implemented. And let's start with a really high level in explaining what the language server protocol is. So it's not made by us, it's made by Microsoft. It's basically a protocol to talk between the editor and the language tool, analyzer, compiler, whatever, to simplify the tooling integration of it, basically. What does this mean? Imagine that we're in a world where there is no LSP or no common protocol of any sorts. When you want to integrate three kinds of languages into three different kinds of editors, you'll basically need 3x3 language integrations because it all depends on the technology of the editor, and it all depends on the technology of the language tool as well. So this is why you get the n times m complexity. Now what the LSP does is it defines a common format, how you basically communicate things between the editor and the language tool. For example, how the editor can ask for completion, how it can ask for diagnostics, or even how the language tool can report errors or anything of that sort. The basics of this is essentially something called JSON RPC, which is a really simple remote procedural call protocol. It's based on JSON, and this is how the dev tool and the language server communicate in notifications or request response format, depending on what the actual message is. And what this allows the implementations to do is to have a really, really small language client side, basically the thing that starts up the language server. It's really, really small. You generally write it in the technology of the editor. For Visual Studio Code, you would write an Node.js application. For Vim, you write it in the Vim extension language thingy. I believe you script it in Lua, at least NeoVim, and you basically just start up the language server, tell the editor where to communicate with it, and the rest should be basically editor agnostic. So let's actually look at an example, and let's look at a very simple language feature just to know what we're talking about here. Let's see, go to definition, something we'll touch on today. There are capability descriptors at the beginning of the specification. Usually, this basically tells us how the client tells us that it supports go to definition, and how the server tells us that it supports or wants to support go to definition. But this is not the interesting part. The interesting part is how you request and how you respond. And here the request is really simple. It basically wants something that looks like this, definition params, whatever that is. I suppose it contains the text position, where we want to look up the symbol, and the response should be all the locations where the symbol is defined, where we pointed at in the definition parameters. To get a little closer to Draco, I tried to draw a diagram. This is drawn on my drawing tablet, so if it's unreadable, I'm sorry. But this is basically the high-level overview of our tooling integration. You have the editors. For example, we have VS Code and NeoVim integrations, but we can really easily add more. And we wrote really, really small extensions that you can see here. I'm highlighting them in green. That basically start up the language server and start the communication with the tool. And these are of course, technology is specific. They depend on how you extend the given editor, what language they're written in, or what they are able to host. But they're also really small, which means that it's not a huge burden to maintain these, because generally all they do is really just boot up the language server and start a communication. Now, the server itself, we wrote it as a .NET tool. This makes it really, really easy to install from CLI. This makes it really easy for us to install it from the extension automatically if it's not detected on your system. This is all implemented in the VS Code extension, for example. And it basically communicates with the compiler API directly. The language server actually ships a copy of the compiler API, so it can provide features for the editor. Now, the communication itself, as discussed before, this is again part of the specifications, is going through JSON RPC. But we needed some helpers here. We didn't want to work with raw JSON RPC and JSON messages. So we created the Draco Lsp library, which is actually language agnostic. So if you want to implement language server in C# or .NET in general, you can actually use this library. It doesn't depend on anything Draco specific, and it makes it a whole lot easier, and I'll show you why that is. Why we decided to make our own: there are existing ones like the one used by OmniSharp, which is called LSP C# or C# LSP, I'm not sure. But we really dislike the existing implementations, and the OmniSharp one as well. It's not an exception here. It was really, really outdated. I believe it's really, really over-engineered for what it should be doing, and it generally just couldn't keep up with the specifications and had these weird extensions that you could do from the outside that were way overcomplicated, and I could never pull one off. This thing actually generates the contracts from the specifications directly, so it's really, really easy to keep up to date. If a new language server version, protocol version comes out, we just paste the specification into our third-party thingies directory and regenerate the contracts for Draco Lsp, which happens automatically with a source generator. Again, this is available as a NuGet package, so if you're a language implementer in .NET, feel free to use this. And just a side note, we have the same thing for the debug adapters. So if you have a debugger that you want to integrate in .NET, we have the debug adapter protocol implemented in a really similar and simple way as well. Let's look at how we implemented the LSP itself. It's just a really, really high-level overview. As you could see in the specifications, they generally talk about capabilities. A capability is a single language or other kind of feature, workspace feature or window feature. A language feature might be something that's related to programming languages, of course. Go to definition, find our references, autocomplete, and window features might be something like show a message to the user, and they are generally things that are not closely related to the programming language itself, but they are nice to have in the language server sometimes. Now, how the LSP is structured is basically we have a source generator that compiles all the TypeScript notations, or I think we're working from the JSON and annotated files now into contracts. I believe I can show that to you through here. This is the LSP one. So here's all the contracts that we extracted from the specifications. You don't have to type any of this out. We keep all the documentation, so the docs are right here, untouched. And we tried to keep all the other annotations as well as best as we could. Apart from this, we of course define how the messages are read from a channel. This can be found basically in the server and the lifecycle thingies. I won't go into this too deep because generally we factored out an RPC package that basically implements a subset of JSON RPC that the language server protocol and the debug adapter protocol needs. And we didn't bother making it a full-fledged JSON RPC implementation. So I won't dive too deep into this. What I want to dive into is how you define capabilities, because I believe that's really, really simple compared to what the OmniSharp implementation does. So for example, if you want to define the capability go to definition, let's actually look that up in the specification. Go to definition. You have the capability. You have the registration options, which is basically dynamic capability registration. Then you have the request and the response. And the specification also tells you what the name of the method is when it's called, what parameters you get, and what you should return. And implementing it is really, really simple. We can just tell that the client-side capability is defined in this structure, which the client sends us at the beginning of the communication. This is how we tell what our capabilities are. If we want to support dynamic registration, we can tell it as well with the registration options attribute. You have both options basically, but generally the interface is default to just forward the capability to the registration options as well. It's generally preferred to do dynamic registration because it's more flexible. So most of the things will use that, but the LSP implementation that we made is capable of doing both. And finally, the request itself is annotated as well. You can see that the method name that you saw in the specs is here. And then we have the method signature. This is what we return. And then we have the parameter, and we support a cancellation token optionally in the capabilities. Because we wanted this to be a generic reusable package, we put cancellation token for basically every request. If there are any questions in the meantime regarding this, feel free to ask away. I'll try to find some other kinds of capabilities as well, not just requests, but notifications. I'll try to see if we have any. Oh yeah, for example, towards the language client, which is basically sending messages to the editor. We have a few notifications, for example, publishing the diagnostics. We don't expect anything in response, so it's just a notification. And it's the same with show message and log message, which are basically just logging capabilities built into LSP. Now, let's look at Draco Lsp, or the Draco language server. It's a really, really simple implementation. Here's the main program that basically just boots up with the given communication channel. Generally, we only support STDIO currently, so the server reads from its standard input and writes the responses to its standard output, and the language client works the same way from VS Code. Generally, you could do HTTP and pipes as well, but STDIO works for us for now. I don't see any reason to change it. And the main thing is here, running the server, which is just setting up the transport stream. It's basically an STDIO duplex pipe. And we instantiate the client proxy, which will communicate with the client. We instantiate the server itself, and we start the communication with calling run async on the client. After that, basically the messages will arrive in Draco language server, and it will implicitly report all the capabilities that we implement on it. There's no need to explicitly register any capability that the server has. Whatever capability the server class implements, it will have those capabilities. We have separated those out into partial classes. So for example, go to definition is basically go to definition implemented on the language server. We implement all the required members. For example, we just implement the registration options and the go to definition async itself. So this will be reported when asked about the capability, and this will be called by the communication handler code whenever a go to definition message comes in from the editor. Now, again, let's remind ourselves the problem that we're trying to fix today. I believe if there are no questions about the tooling anymore, we can actually tackle the problem itself. Is that we have go to definition available for every method here except the ones that are generic. That's because these are generic instances, so the language server is too stupid to realize that it needs to look for the generic definition. And I believe it's the same way, the same thing the other way. If I go to references, it will find this singular reference for all these methods. But if I try to find all the references, I'm not sure that it will find anything. No, it does not. So these are the two basically capabilities that we want to fix today in the language server. And let's start with go to definition, as it's really, really simple. I'll quickly walk you through the code. We stash the compilation here. We generally do that before every language server operation. This is because the compilation can actually change in the meantime, and we don't want to give inconsistent results, so we make a local copy of the compilation. Just a side note that in language server world, everything is highly parallel because a request might not complete, or the billions of requests might not complete at the same time, or they might not complete before another update comes in that you have to respond to. So you'll have to get ready for that. We basically request the syntax tree that is currently open. Basically the parameter for definition params tell us which file the definition is requested from. We can request the syntax tree based on that. We have some error handling code in case we cannot find it. And if we do have it, we ask for the semantic model of the compilation. If you're familiar with the Roslyn API, it's basically an interface for requesting symbolic and type information. We also translate the cursor position that came in the parameter to a compiler syntax position. We have a translator layer because the compiler and the language server protocol obviously have different structures for the same things. For example, they have this position structure that if we peek into, it's a line and a character. And on our side, we have an API syntax position, which is a line and a column. They look very similar, and the translation is very trivial, but still they are not the same structure. So we have a translation layer. If you look at the translator, most of the translation is pretty trivial. We only have a couple of edge cases that we handle here. After that, after we asked for the semantic model and the cursor position, we basically walk down the tree, the syntax tree. This is a utility method that walks down on the given position, looking at every basically subtree, and it tries to query the semantic model for the reference symbol for that syntax. And we take the last one that is not null, assuming that we want the reference symbol for that one. And if it's not null and it has a definition, then we can return that as the definition location. Now, the fix for the go to definition is really, really simple, because we can just ask if this reference symbol is a generic instance, and if it is, then we can just say that let's not look at the generic instances definition, let's look at the generic definitions definition. Now, the problem with that will be is that we currently wrap the symbols, the internal compiler symbols, into a really thin public facade, which does not yet contain any generics, so we're just going to hack it in there really quickly. This can all change later, so we generally don't really care about what's inside this facade layer yet. It's just there, so we have the API decoupled from the compiler internals. So what we could do is have something like public bool is generic instance, and we don't have an implementation for that yet. Copilot is really good at guessing these really simplistic API doc comments. And then we can have a public I symbol, generic definition. Good. Maybe you could do something fancy. I'm not sure if this will work, but let's try it. Is it member, not null one? Yes, it is. Let's see if this will actually work. What I'm trying to tell the API here, or Roslyn rather, is that if this is true, this should not be null, so we can omit the null check. And you'll be able to see here that we basically have a single implementation, single actual implementation for this for these facade symbols, and we generally hack everything into here, and subclasses are just really small wrappers around this. So we can implement the remains of the interface here, and it's hopefully really simple. What we can do is call this, because the internal symbol already has its generic instance property, and for the generic definition we have this, and unfortunately that's an internal symbol, but we have a translator. We just call to API symbol, and that can be null, so let's do this. And this should be it for the compiler API changes, actually. So now we can go back to the language server capability implementation and check if the reference symbol is a generic instance. Oh yeah, if it's not null. Actually, let's refactor this code a little bit, because we already do a null check here. So what I want to do here is, if the reference symbol is a generic instance, we'll very simply unwrap it like so. That should be all, I believe. Why are we erroring here? Oh, because we're not always returning. Yeah, we can just remove the else here. Or we could be smarter and invert this conditional. This might be nicer to read because I generally prefer guard statements, so keeping the happy path just linear and then have these opt-outs in case anything goes wrong and we don't even need this if anymore. Oh wait, yeah, but here sadly we have yet another case. Yeah, because here the definition is checked for the generic thing. So we might just revert the changes I did. And for now, we're just going to accept that we cannot win every war. And we'll stick to this one for now. Possibly null. Oh yeah, because I think I didn't revert far enough. Yeah, this is how we should write it. So, but wait, why do we not need the double null check here? Oh, I know why. Let's leave it like this. We'll refactor it later. So how you test the language server is that you can actually install it from source code. I've shown this the last time, but in case you missed it, in the compiler root, we have a directory called scripts, where we have a bunch of PowerShell scripts that help you during development. One is called install lang server that basically installs it as a .NET tool globally for your PC, which means that the VS Code extension will use it. So let's try it out. Unfortunately for that, we'll need to close Visual Studio Code because otherwise the tool is still in use and it won't let you to install it. So let's run the script to install it. Okay, and let's restart the VS Code instance that we had with this code. It takes a second to start up because of a bunch of things. Okay, it started up. So this one still works, this one still works, and now this one works as well. Wonderful. So we fixed go to definition. And of course that didn't fix find all references, but we're going to work on that in a second. First off, let's try to refactor this code to be a bit smarter. We could actually try something like this. Did it include something that it should not have? It went haywire with all these location thingies. It generally happens when it insists on giving bullshit usings. I believe it's API diagnostics that's the problem. Okay. And let's do it like this. I'm not a fan of how we do this but it's going to be fine. Let's try it out. Hopefully it still works. It was just a small refactor. Yep, these still work. Wonderful. So now let's tackle find all references, which is just a bit more complicated. It's not that much worse, but actually first let's commit what we've done. And now we're going to the find all references capability. Again, we define the registration options, which is the dynamic capability registration flow. And then we've defined the method itself, which is, again, not too complex. We first, again, stash the compilation because it's kind of volatile, meaning it can change during this request. We request this syntax tree where the definition can be found. Again, that's part of the parameter here. We request the semantic model to be able to inspect types and symbols. And we basically try to find this symbol that was pointed at. Here the difference is that we look at both the referenced and the declared symbol as well. This is because we allow you to click here for all the references. This will find all the references for this. But we also allow you to click here. So basically, we look for either a referenced or a declared symbol at the cursor position. And if we found a symbol, we find all the references in the compilation, which is really stupid right now. But what it does is that it goes through all the syntax trees in the compilation and in all nodes and checks if it references the given symbol. Now, let's see where we can insert our little hack here. So we're probably going to need to insert it here as we do the equality check here. So maybe what we could do is let's include one more property in the symbol API called isGenericDefinition, which is basically if it's a generic thing, it's not an instance of a generic thing, but it is the definition for it itself. And let's implement it in the symbol base. And the implementation will be really simple for this as well, because you'll never guess. We already have the property in the internal symbol. We just need to expose it. And then we could do something like, let's do it in this method. Actually, we don't need to do anything here, but we could check if the is a generic definition. Then we also need to look for generic instances for this. And how we're going to do that without ruining the currently very simplistic flow is I have no idea yet. Maybe we could do something like so. First off, let's factor this out into a variable. And let's rename this to something like surged symbol. And we could also factor out a method, something like private static bool is surged symbol. This should be fine. Yeah, search dot equals found the generic definition. That should be fine. Otherwise we return false. And we can basically replace all this logic with this. Oh, it's missing a null check. Hopefully, this should have smartened it up enough to now find the generic instances, and we could keep it relatively nice. So again, let's close VS Code to be able to install the tool. And let's see. So let's find all the references. Oh my, we found it. Let's look for the other one. Let's actually duplicate this a few times to see if this isn't a fluke. Awesome. We got full navigation again, even in generic contexts. That's pretty freaking awesome. Also, let me show you something really cool. You can actually debug the language server in something like Visual Studio. You can also do it in Rider. What you basically do is you place your breakpoints or any setup you need to do, and you can basically attach it to an existing process, and you would look for the Draco-lang server. You attach, and it's basically attached to my single running VS Code instances Draco Lsp. So now if I try to do something like find our references, why did my breakpoint not hit? Oh, is it because we have some version incompatibility? I'm not sure. Let's try to reattach. Interesting that we're not. For some reason, we're not ever hitting this breakpoint. This is something we'll have to look into, because you used to be able to really simply debug the language server. Anyway, with that, I believe we have fixed find our refs as well. So let's commit that. And if there are any questions about today's session or about the language or tooling in general, feel free to ask away. In the meantime, I'll grab a glass of water. Okay, no questions. I believe this was a short session as well. I'm not sure because Twitch is not telling me how long we've been live. I'll need to check that. But I can promise you that the next time or the next project that we'll tackle on live stream will be a bit more interesting. I hope it will be more interesting to a more widespread audience. We'll start implementing the REPL for Draco as a .NET tool as well. So we'd be able to execute stuff line by line and carry on the context of the previous execution. It should be interesting enough, and it's probably going to be a multi-part effort, but we'll see how it goes. So thank you everyone who joined in. The VOD will be available soon on YouTube as usual, and take care. Bye guys.